All right, now that you guys know whether a molecule is polar or nonpolar, now we can talk about how that affects the way molecules interact with one another. So section 4.3 is what we call intermolecular attractions. All right, we're going to talk about the ways that molecules attract each other if they attract each other. So first off, here we see samples of three states of matter, right? We've got our gas, our liquid, and our solid. Now, whatever state of matter a substance has at room temperature, so room temperature meaning like our temperature that we're in right now, around 20 degrees Celsius, whatever state of matter something's in depends on the strength of attractions. So, gases are particles that are very far apart. They're always moving. They're not very strongly attracted to each other, which is why they're separated from one another. The reason why they're not attracted to each other is because the attractions they have just aren't very strong, and this has to do with molecular polarity. Liquids have decently strong attractions, and that's why they stick to each other. They cling to each other. They can move around, and they can wiggle, and they can, migrate all the way through the liquid. The attractions are decently strong. In a solid, the attractions are so strong that all of the molecules are held in place and cannot move. So solids will have the strongest intermolecular attractions. Okay, so we're going to go over the types of interactions that cause things to be solids or liquids or gases. Okay, so first, two terms we have to get out of the way. There's inter and intramolecular attractions. So the term intra refers to within. They are the attractions within, as in inside a molecule. They are the attractions that hold the molecule together. I.e., bonds, but specifically covalent bonds. So any one of the Lewis diagrams that we've drawn so far, right, any of these, when we say intramolecular attraction, we're literally talking about these guys. These polar covalent bonds are what we call intramolecular forces. So, molecules can attract one another, and when they do, those attractions are what we call intermolecular attractions. Right? So notice the difference in the word. Inter versus intra. These are attractive forces felt between separate molecules. So, for example, if a water molecule attracts another water molecule, that's what we call an intermolecular force. And that's what we're focusing on today. Now, in that water molecule that I just drew, it's a molecule, so that means it does have covalent bonds within. So these are still intramolecular forces because they're bonds. And by the way, intramolecular forces can be polar covalent or just nonpolar covalent. Any kind of covalent is what we call intra. All right. You have a bunch of molecules in a sample. Would you guys be able to distinguish between the intra and the intermolecular force? Another way to think of it this, your parents ever go out with a group of other friends who are also parents, right? So the relationship that your mom and dad have, they're married, right? That's like the intramolecular force, right? That's stronger than the friendship that your parents might have with your neighbors. Because your neighbors might be married, and your parents might hang out with the neighbors every now and then, but the stronger relationship is the one that holds the marriage together. So the bond is like the marriage, and then here, your parents hanging out with your friends' parents, that's a friendship. But that's not as strong as what holds the atoms together. Does that make sense? There's both attractions, but one is considerably stronger than the other. The intra is many times stronger than the inter. Let's actually write that down. So okay. So we'll be using this word intermolecular attractions a lot, and we'll be abbreviating it just as IMAs, intermolecular attractions, okay? Because it's a long word to write, and we're going to be writing it a lot. So let's talk about this theory. It's called the kinetic molecular theory. And it can be pretty complex, but we're just going to focus on the part that we need to know here. And I think it makes a lot of sense. In general, if substances have weak intermolecular attractions, then that substance is going to be a gas. So, on the periodic table, remember how we talked about color coding of the elements? How there's red, black, and a couple blue? The red are gases, the black are solids, and the blue are liquids. So, the gases are things like noble gases, or nitrogen, or oxygen, or hydrogen, or chlorine, or fluorine. Those will all have weak intermolecular attractions. That is why they are gases at room temperatures. Okay. Moderate intermolecular attractions will be liquids, right? And the liquids are blue on the periodic table. So the two that jump out right at the top of you are bromine and mercury. And then if they have stronger intermolecular forces, they're solids, they're black. Okay. So that's just generally speaking, but let's actually talk about what these forces are. Well, actually, before we do that, here's another picture. So this is oxygen. So this is an oxygen molecule, and so is this. Here's another one. Here's another one. Here's another one. These oxygen molecules can be attracted towards one another at really, really, really cold temperatures. I don't know if you've ever heard of liquid oxygen, right? Sometimes there's a liquid nitrogen or liquid oxygen that's necessary to keep things really, really, really cold. And I mean like negative 230 degrees Celsius cold, which would be about, negative 450 degrees Fahrenheit cold. Really, really, really cold. Okay? So, these oxygen molecules, they have very, very weak attractions here. And because their attractions are so weak, the only way to get the molecules to stick to each other is to lower the temperature a lot. So liquid oxygen only occurs at really, really low temperatures. But if you raise the temperature to room temperature, it's definitely a gas. So you can pretty much put it this way. You can pretty much condense anything or freeze anything if the temperature is low enough. Water can be frozen. At room temperature, water is liquid. You can freeze it, but you got to lower the temperature, right? At the same time, you know that water vapor, steam, humidity can be turned into a liquid by lowering the temperature. So you can actually take steam to liquid to a solid just by drastically reducing the temperature all the way. Okay, so again, the point of this picture here is for you to be able to identify, like if I gave you a diagram like this, could you point to the lines, the black lines or the gray lines, and identify them as either intramolecular or intermolecular? The intra are the stronger ones that hold the molecules together. The inter are weaker. Okay? All right. So let's talk about the types. The first three types we're going to be talking about are here. They're intermolecular attractions. And these are the attractions that take place within covalently bonded compounds. Okay, so they only apply if there are covalent bonds involved. If a substance has ionic, right, or if they're metals, then these do not apply to them. Oh, wait, hey, I just did that right there. Okay. All right, so the first type is what we call dipole-dipole attractions. So first of all, a dipole is a polar molecule. So in other words, this is the attraction that takes place between two polar molecules. So you would have to know that the molecules are polar, and how would you know that? By drawing the Lewis diagram and figuring out its geometry. Remember that if you have a polar molecule, and we'll draw a simple one here. If you have a polar molecule, you have a partially positive and partially negative side. Polar molecules will actually stick to each other, or they'll at least attract each other. But you have to pay attention to the sides. They're the correct side. Oops, I did not, because that is wrong. Hold on, let me fix this. The negative side is attracted to the positive side of another molecule. Opposites attract. This has always been true. Okay? If two molecules with the same side face each other, it just flips around. So if you draw a bunch of these, you have to make sure that you have the correct side facing each molecule. And this type of attraction is what we call a dipole-dipole attraction, an attraction between two polar molecules. Now, because of this, they have to align, and that's what I was just talking about. The positive side lies next to the negative side of another. Now, these alignments aren't perfect because they all wiggle, they all move around, but whenever they can, they will arrange themselves this way, right? Granted, if they're moving around. Just a dipole-dipole attraction is only about as 1% the strength of a covalent bond. So just to give you an idea, we said it was stronger. How much stronger? This much stronger. Okay, covalent bonds are about 100 times stronger than this dipole-dipole attraction. Okay, so big difference. And again, how will you know if molecules have this attraction? If you decide the molecules are polar. Okay. Some other pictures. Here the attraction would be between these two molecules, right? Here's a bunch of them all aligned. Now, of course, the shapes of molecules can vary. As you've seen, there are bent, there's trigonal pyramid, there's all sorts of different shapes. We're just kind of drawing the simplest ones right here, right now. But the point remains, whatever shape it is, they're still going to align themselves negative side to positive side. Okay, here these are just simple shapes, but you know that there are more shapes than this. You guys okay with dipole-dipole attractions? You just need to know if the molecule is polar. And then this is the attraction it has. Okay. The next type is what we call hydrogen bonding. And this is actually a type of dipole-dipole attraction, but it's a special, stronger version of it. All right, and so it's got some requirements. So first, this only occurs when hydrogen is directly bonded to one of these three elements: nitrogen, oxygen, or fluorine. Okay, NOF. So here's what happens. I'm going to insert a page here just so I can draw this in detail to help explain it. Okay, so let's say we're talking about hydrogen fluoride. The reason why hydrogen bonding only occurs with fluorine, oxygen, and nitrogen is because they have very high electronegativities. And so what that does is, if you recall, hydrogen is just a proton and an electron, right? One proton, one electron, that's it. So when fluorine bonds with hydrogen, the fluorine's electronegativity draws the electron towards it to the extreme. So what that means is the fluorine has the electron virtually all of the time. Let me color code that differently. Oops. Okay, so let's say here's fluorine's valence electrons, right? Fluorine has 7 valence electrons. And so let's say that this green electron was from hydrogen. So if that electron from hydrogen is pulled away, how many electrons are circulating around the nucleus of hydrogen? Yeah, basically none. That electron is basically gone. And so now we have this really, like this positive charge. It's like a beacon. It's a very, very strong positive charge that is unshielded. And because that side of the molecule is so positive, it strongly attracts the negative side of molecules more than usual. So we write a huge delta positive there. So then other molecules are more attracted to it than a normal dipole-dipole. What I'm trying to convey to you is that hydrogen bonding is a very strong type of dipole-dipole attraction. Stronger than the typical dipole-dipole attraction. It's actually about 5 times stronger. It gets its own category. But it only happens, you have to meet the criteria, hydrogen bonding only occurs first in polar molecules that have hydrogen bonded to either F, O, or N. If there's no F, O, or N involved, then there's no hydrogen bonding. The H has to be directly attached to one of those three elements. So let me give you some more examples and some non-examples. Example. Water. Remember the shape of this? There's two bonds and two lone pairs. You're going to need to know the shape for the quiz next week. It is bent. Is this polar or non-polar? It is polar. Okay. Is there H directly bonded to oxygen? Yes. Yes. So this has hydrogen bonding. What does hydrogen bonding look like? It looks like this. And this is important to understanding. Hydrogen bonding is the attraction between the negative side of the molecule and the positive side of the molecule, which basically means it's between the oxygen. So you've got to find the oxygen, which is the negative side, and it's here. Right there. Remember that the hydrogen is very, very positive, right? And so the oxygen clings to that hydrogen strongly like a magnet. And this is actually the reason why, even though water is one of the smallest molecules around, water is a liquid. Most molecules that are as small as water are a gas. Okay, here's a non-example. This is called Difluoromethane. It's used as like an aerosol in like hairspray cans and stuff like that. You guys use hairspray ever? Sometimes? Yeah. It was big in the 80s. Girls would go through like 2 cans of hairspray a week, just like spraying their hair, making their hair stand up for some reason. Kind of looks like an animal, like perched on their head, but when the time they were done. Anyways, so is this a polar molecule? It is polar. It is polar because it's even though it's tetrahedral, you don't have the same atom in all directions, which means your electrons are not distributed perfectly in every direction. But is hydrogen directly attached to fluorine? No. Hydrogen is attached to carbon. Fluorine is attached to carbon. So no H bonding. And that is a critical difference. So you have to look for that, okay? Just because a molecule has both H and F or H and O or H and N, it doesn't mean it's automatically hydrogen bonding. You have to see where they're bonded. Okay. So these molecules, because they're just polar, these would have dipole-dipole attractions. Which are not as strong as hydrogen bonding. Let me give you another example of hydrogen bonding. This molecule is called ethanol. Ethanol is derived from corn and is often used as an additive for fuels. Sometimes when you go pump gas, it'll say, it'll give you an ethanol rating and it'll say up to 10% ethanol, right? So this molecule, even though I drew it like a straight line, if I sent you in lab and told you to build this with the balls and sticks that we used in our last lab, you would see that this H is actually, it's not a straight line. It's actually kind of bent this way because of those angles. And that bending makes this polar. H is directly bonded to O, which means this has hydrogen bonding. This is what we call an alcohol, and all alcohols have this. They all have this OH slapped onto the end there, and that makes it polar, and it makes it have hydrogen bonding. So in the future, if you ever see a formula that's got a bunch of C's, got a bunch of H's, but then ends in an OH, you know automatically that it has hydrogen bonding. Okay? Another example. I'm sure you've seen this from biology. What is it? That's glucose. Glucose actually has lots of hydrogen bonding, right? It's a sugar. And the way that you tell what a sugar is the number of C's matches the number of O's. And H's are roughly twice the number of carbons. So if you see a formula that meets this criteria, it's got a bunch of C's, but it's got twice as many H's, and the number of O's is about the same as the number of C's, that's a sugar. And sugars have lots of hydrogen bonding. What state of matter is sugar? Yeah, it's a solid. Okay. So far we've discussed two types of intermolecular attractions. Dipole-dipole attractions occur between polar molecules. Hydrogen bonding occurs between polar molecules that have H directly attached to O. So let's talk about the third. But before we do that, let's look at more pictures. Here's water. Here's where the hydrogen bond exists. All right, that picture makes sense. Could you draw that if I asked you to? Draw a water molecule. You know that the hydrogen side is positive, the oxygen side is negative. How do I know in a water molecule that the hydrogen side is positive and the oxygen side is negative? What value could possibly lead you to remember that? What value could possibly lead you? The electronegativity, right? The higher electronegativity is the negative side. Okay. And here's a busier picture of a bunch of water molecules, right? All showing you how they attach. Okay. When we're dealing with hydrogen bonding, the main molecule that we keep coming back to is water. And so the thing about water is that because water forms hydrogen bonds, there's a very specific angle that has to take place. And this angle causes them to spread out very uniformly, but also very specifically, where once you get into the solid form, the hydrogen bonds form the water molecule in a lattice. Remember we used a lattice before? Right? We said lattice was a regular repeating structure. And solid water is less dense. Solid water is less dense. That's why ice cubes float. because ice cubes are solid water and water is liquid. The heavier things sink to the bottom, lighter things float to the top. Well, the solid, which is ice cubes, are floating at the top. They're less dense. The reason why they're less dense is because, imagine, you guys ever form a human pyramid? Like you get like 20 people or 10 people or whatever, and you got like a base layer of maybe like 5 people on the ground, and then you get like another layer of like 3 people leaning on the people who are on the ground, and then maybe 2 and then 1. Okay, when you're in a pyramid, your arms are stretched out, right? So the total volume of people in a human pyramid is greater, and density is mass over volume. But what happens, invariably, what always happens to a human pyramid after like 35 seconds? They all fall. So you go from something like this, you got these people kind of arranged. Right? But then, so this would represent a solid. Right? But then everybody gets tired. And they fall down. And so now you just have a human pile, not a pyramid. What's the total amount of space you take up when everybody falls? There's less volume. So your density, which is equal to mass over volume, now this is a lower volume, which means the density is higher. This is like liquid. Kind of a crude example, but when things spread out, they are less dense, is the point. And this has to do with the hydrogen bonding that is taking place in water molecules, because the hydrogen bonding forces water molecules to spread out. That's why it's less dense. Now, hydrogen bonding does not make everything less dense. We're just kind of talking about water here. Okay? All right, so the last type of attractive force today is what we call London dispersion forces, or just dispersion forces for short, or London forces for short. So, dispersion forces are the only intermolecular attraction that exists in nonpolar molecules and unbonded atoms. So, before I read this, let's just look at a couple pictures. Okay, here's a small atom. In this atom, the electrons in that atom are roaming around freely and independently. Wherever one electron goes doesn't have anything to do with what the other electrons are doing. Okay, so imagine, a track around the football field, right? If everybody's running, it's not like if you start at opposite ends of the track that you're always going to stay the same distance apart, right? Eventually, you might be clumped up, but you might spread out. You might be clumped up on the left side or on the bottom, or you might spread out. It's kind of random. So electron movement in an atom, in a molecule, is random. So if it's random, then what happens is this. Occasionally, your electrons will be skewed towards one side more than the other. And if that happens, the left side is partially negative, but only temporarily, briefly. That atom, which is normally nonpolar, is just, for a very short time, polar, because the electrons ended up on one side. But the electrons, because they're constantly moving, will average out and come back here, and they will be equally distributed. And when the electrons are equally distributed, you know that to be nonpolar. So it's constantly the shifting back and forth. Here's another example. If the electrons here in this atom kind of just end up towards the left side, the atom that's next to that atom, its electrons are going to be pushed, because the electrons here on this atom repelled the electrons in this atom and pushed them off to the left. So they can actually influence each other, temporarily causing an atom and its neighbors to be polar as well. But the key point is that this is very, very temporary. These are not normally polar molecules or atoms. They are only polar temporarily. The electrons are constantly shifting, and as they constantly shift, they go from being nonpolar, polar, nonpolar, polar, nonpolar, polar. So those attractions, they don't last constantly. Kind of like a little kid turning on and off the light in a room. Is the light always on? No, but if he's flicking it on and off, on and off, on and off, on and off, that's kind of the same thing that's happening with dispersion forces. The attractions are there, then they're not. They're there, then they're not. They're there, then they're not. Over and over again. So, okay. It's based on random electron movement. We call these instantaneous temporary dipoles. They can induce electron movement in a neighboring atom or molecule. But again, the key, temporary, instantaneous, right? It's not lasting. So, all atoms or molecules have dispersion forces. They are found in everything. But what we're trying to get across is that it's the only attractive force that nonpolar molecules have. A molecule that's polar or a molecule that has hydrogen bonding has those forces and dispersion forces. So they're like doubled up. Okay, but these guys, nonpolar molecules, the only force they can have is dispersion forces. All right, so dispersion forces they can actually add up, and they can actually be decently strong if there's a lot of them. So what determines the strength of dispersion forces is the number of electrons. The more electrons, the easier it is to form dipoles, the stronger the dispersion forces will be. You know what? I'm going to cross this statement off here. I don't like this. All right, let me give you a different example. This molecule is called propane. Now, propane is what you use in a grill, like an outdoor grill. Okay, so it's actually a gas at room temperature, and that's why it has to come in a tank. You hook up a valve to your grill, and you open the valve, and then the gas flows, and that's what feeds your grill fuel. This molecule is called octane, and it's got more hydrogens and more carbons, right? This is known as gasoline. What state of matter is gasoline? It's liquid. Looking back at this first molecule here, this propane, would you characterize this propane as polar or nonpolar? It's nonpolar. It's definitely nonpolar. Remember, does any side of it look different? Is there any different atom on the left or right pulling electrons more? No, it's perfectly nonpolar. Okay, look at the gasoline molecule here, C8H18. Would you say that it's polar or nonpolar? It's also nonpolar. Okay. Both of these are nonpolar. But this one is a gas, this one is a liquid. Because they're both nonpolar, they both have dispersion forces. Because that's the only attractive force that nonpolar molecules can have. But one of these is a liquid, one of these is a gas, which means one of these has stronger attractions than the other. What is the difference between these two molecules? Well, what if I asked you to count up the electrons? I said, all right, look at C3H. Carbon is element number 8. Right, so this is going to have 3 times 8, so 24 electrons plus 8. So this has 32 electrons. What if we counted up the electrons in gasoline? So 8 times 8, 64. 64 plus 18, 82. 82 versus 32. The more electrons something has, the more dispersion forces it has. Therefore, it's got stronger attractions. Okay. So I think this is a good place to stop here. You know what? Let me just give you a couple more examples, then we'll stop. Just to drive this home here. Okay. The first molecule. There's 3 intermolecular attractions we just talked about. Which one is the first one going to have? It all starts with you identifying if the molecule is polar or nonpolar. That is the first thing you must ask yourself. Okay, nonpolar, yes. If it's nonpolar, that means the answer is simple. Dispersion. That's it. Once you identify it as nonpolar, that's the only thing it can have. Okay, let's look at the middle one. Is it polar or nonpolar? It is polar. That puts it in the dipole category, but there's 2 types of dipoles. There's regular dipole-dipole, then there's hydrogen bonding. This is hydrogen bonding because it's polar and it has H bonded to N. That means it has hydrogen bonding. SO2. It is polar. Does it have hydrogen or nitrogen or fluorine? It has oxygen, but there's no hydrogen, so it doesn't matter. So this is just dipole-dipole. So if I give you some formulas, you would need to draw the Lewis diagram, or maybe, maybe not draw it if you can see it. Like F2, I don't know if you need to draw that, right? You need to figure out whether it's polar or not. And then figuring out whether it's polar or not is the first step in determining which of the attractive forces it has. Okay? I'm going to give you a homework, and on the homework there's a couple of extra forces on there. I just need to point them out. We didn't talk about this today, these two today, but we'll talk about them later. There's metallic forces, and that's found in metals, and that's pretty straightforward. So if I said, what type of forces does Fe have? You would look up Fe, you'd see it's a metal, and you say, oh, it's got metallic. Okay, so that's pretty straightforward. And then there's ionic, and with ionic, you are looking for a combination of a metal with a nonmetal. Right, so NaCl, CaBr2, and so on. Polyatomic ions even, KNO3. There's a metal and there's a polyatomic ion. That's ionic because it's got ions in it. All right. That's good enough for today.